Last time, we settled Bobcha's $11 question. Direct orders really were worth more. Today, we ask a completely different kind of question. Not is the gap real, but can I use one number to guess another? Study hours and an exam grade, height and weight, square footage and a house price. Whenever two things tend to move together, is there a rule hiding in there? One number in, a prediction out? That's simple linear regression, and it's also the last new idea of the whole course. This is Week 5, Lecture 18, fitting a line through a cloud of points to predict.
So picture the two things you're comparing as pairs, study hours and a grade, say, and you plot every pair as one dot. Do that for a bunch of students and you get a cloud. Not a random blob, a cloud that leans, that has a direction.
And the picture on screen shows exactly that, a rising cloud of dots and a line drawn right through the middle of it. That line has a name, y hat equals b-naught plus b1x, and the whole lecture is about how you find that particular line and what you do with it once you have it. Regression turns a scatter of dots into a rule for predicting.
Formally, we model the response y as a straight line function of a regressor x plus random scatter. Y equals beta-naught plus beta-1x plus epsilon.
Beta-naught is the intercept, beta-1 is the slope. Together, the regression coefficients. And they're unknown. We estimate them from data. Epsilon is random error, with mean 0 and variance sigma squared. That's the residual variance. Worth separating the two rules here, too. X is deterministic. We set it or observe it directly. Y is random. It scatters. If epsilon happened to be exactly 0 every time, y would equal beta-naught plus beta-1x exactly, a perfect line. Epsilon is the reason real points miss it. And if you had several regressors instead of one, this becomes multiple regression. Same idea, more x's.
So the betas are unknown, and the entire game today is estimating them from a sample.
Here's a subtlety worth sitting with. At each fixed x, y isn't one number. It's a whole distribution of possible values. But those distributions have means. And here's the key fact. Because epsilon averages to 0, the mean of y at x is exactly beta-naught plus beta-1x. Mu, given x, equals beta-naught plus beta-1x.
That's the true regression line, the line of means. Look at the picture. At each x value, there's a little bell curve of possible y's, and the dot marking each bell's center sits right on the line. Same spread, sigma, at every x, just the center slides along the line.
In real life, we never see that true line. Beta-naught and beta-1 are unknown constants of nature. All we ever see is a sample, m pairs xi and yi, plotted as a scatter. Home price against square footage, mileage against engine size, oxygen level against water temperature, exam grade against study time.
And the picture shows the pattern, m dots with an obvious upward trend, and a dashed line hinting at where the fit will land. M is just the sample size. The cloud hints at a line we haven't fit yet. Wherever one quantity tends to move with another, a line may summarize the trend. So, which line is best? Here's the idea. For any candidate line, y hat equals b-naught plus b1x. Each data point misses that line by some vertical amount, the residual, ei, equal to yi minus y hat I.
And you don't want misses that cancel. A residual of plus 10 and one of minus 10 shouldn't look balanced. So square them and add SSE, the sum of EI squared. Least squares is exactly the rule. Pick b-naught and b1 to make SSE as small as possible. Look at the picture. Each dashed segment is one residual, and least squares is squeezing all of those segments down together.
Minimize SSE, a little calculus, and outcome closed-form formulas. The slope, b1 equals m times the sum of xi yi minus the sum of xi times the sum of yi, all over m times the sum of xi squared minus the sum of xi squared. Equivalently, the sum of xi minus x bar times yi minus y bar over the sum of xi minus x bar squared.
And once you have the slope, the intercept falls right out. b-naught equals y bar minus b1 times x bar. So the fitted line is y hat equals b-naught plus b1x. b1 tells you how much y hat rises per 1 unit increase in x. b-naught is just where the line sits at x equals 0. And a nice fact, the line always passes through the point of averages, x bar, y bar.
So in practice, you only ever need 4 numbers, 2 sums, xi times yi and xi squared, and 2 totals, the sum of the x's and the sum of the y's. Everything else is arithmetic.
Let's actually do it. 9 students, their midterm score, xi, and their final score, yi. Can the midterm predict the final? Here's the table of 9 pairs. Midterms from 50 up to 99. Finals from 34 up to 99.
With m equals 9, the 4 sums, the sum of the x's is 707, the sum of the y's is 658, the sum of x squared is 57,557, and the sum of xi is 53,258.
And the 2 averages fall right out. X bar is 707 over 9, 78.56. Y bar is 658 over 9, 73.11. Everything from here on flows from these 6 numbers.
Plug the 4 sums into the least squares formulas. B1, 9 times 53258 minus 707 times 658 over 9 times 57557 minus 707 squared. That's 14,116 over 18,164, 0.777.
Then b-naught, y bar minus b1 times x bar, 73.11 minus 0.777 times 78.56, 12.06. So the fitted line is y hat equals 12.06 plus 0.777x. And on the right, that's exactly what you see, the line running right through the 9 points, catching the upward lean. Now use it. Suppose a student scores 85 on the midterm. What final does the line predict? Y hat equals 12.06 plus 0.777 times 85.
12.06 plus 66.05 is about 78, so a midterm of 85 predicts a final of about 78. Reading the pieces, the slope, 0.777, says each extra midterm point adds about 0.78 to the predicted final. The intercept, 12.06, is just the line's value at x equals 0, not literally meaningful for a midterm score since nobody scores 0 and stays enrolled.
One caution worth remembering, predict only within the data's range. Extrapolating far outside the 9 midterms we actually saw is unreliable. Prediction is just the lines fitted evaluated at a chosen x, and that line's only trustworthy where the data lived.
A line always exists. Least squares will fit something no matter how scattered the cloud is. So the real question is, how tightly did the points actually hug that line? That's what correlation measures. R equals the sum of xi minus x bar times yi minus y bar over the square root of the sum of xi minus x bar squared times the sum of yi minus y bar squared.
R is always between -1 and +1. The sign tells you the direction, positive here, since finals rise with midterms. The size tells you how tightly the cloud follows a line. Our data, R equals 0.561, a moderate positive link, not a tight one.
And R squared is just R squared, 0.315. About 32% of the variation in finals is explained by the midterm score. The rest is everything else, study habits that changed, an off day, material that didn't carry over. At the extremes, R equals plus or minus 1 means the points sit exactly on the line. R equals 0 means no linear link at all. A high R squared says the line predicts well. A low one warns that x alone leaves a lot unexplained.
And if you'd rather skip the sums by hand, GeoGebra's free Two Variable Regression Analysis does it for you. Type the XY pairs into its spreadsheet, select both columns, choose Two Variable Regression, then Linear, and it hands back the fitted line and the correlation directly. Feed it our 9 midterm to final pairs, and it reproduces exactly what we found by hand. Y hat equals 12.06 plus 0.777x, with R equals 0.61. A good way to check your work, not a replacement for understanding it.
So the whole arc of today, start with the model. Y equals beta-naught plus beta-1x plus epsilon. Least squares turns a sample into estimates, b-naught and b1. That gives the fitted line. Y hat equals b-naught plus b1x. Plug in an x and you predict a y. And R squared tell you how much to trust that prediction. And our midterm question got a real answer. Y hat equals 12.06 plus 0.777x. A midterm of 85 predicts a final near 78, with R of 0.561 and R squared near 0.32. A real link, but a moderate one, not a guarantee. And that's the method every single time, no matter the data. Gather the pairs, minimize the squared misses, read off the slope and the intercept, then predict. That's simple linear regression, and it's also the last new idea in this course. Thanks for building all of this with us.